All right, today we are talking about a pretty new paper. It was, well, at least the most recent thing was from August of 25, and this is called A Mathematical Perspective on Transformers by Borzhan Gaskovsky, Cyril Latroy, Yuri Polyansky, and Philip Rijoulet. And so, first of all, there's a table of contents, which is great. I love that. And so, what we're going to be talking about is essentially this idea that transformers are somewhat popular, right? And the thing that makes transformers important is the self-attention mechanism. So that's what we're going to be focusing on. And inside of the self-attention mechanism, what we're going to be doing is we're going to be talking about it is as if it's an ODE. And so we are going to have some initial conditions, x naught. We are going to have some dynamics. And then we're going to say, okay, so we have the initial conditions, we have some dynamics, and we're going to find out where we go from there. And we're going to use the tools of optimal transport in order to get there. And essentially what we're doing as an overview of this paper is you have your self-attention layer. And at the between each transformer layer, there's going to be layer norm. So there's going to be layer norm at the beginning, self-attention, then another layer norm. These two layer norms, we're going to use that in order to say, okay, so we are operating on a constraint that's constraining one of our dimensions. And so we're going to use that, as well as the idea that our Q, K, and V, as well as the O, but we're not going to talk about the VO. Just Q, K, and V are all going to be taken as the identity matrix, just for ease of use. You train a neural network, oh wow, everything turned out to be identity. That's pretty cool. That's pretty convenient. And inside of that, we're going to say, okay, these three matrices, as well as the layer norm constraints, are going to mean that we are operating on a hypersphere. So there's going to be some activations, or we take it as tokens, I think. There's going to be n tokens throughout the paper, but you can just think of them as generalized activations. It really doesn't matter. We're making very few actual connections to what we actually see in the real world with trained networks. They do say that it links to token uniformity, oversmoothing, and rank collapse, but that's an aside. And so you have these activations coming in, and they are going to be constrained onto our hypersphere. And then there's going to be some evolution of these particles. And this is what we're going to be doing with our dynamics. We're going to be using optimal transport. You have some initial distribution of particles, and you have some end distribution of particles. And then the movement between these two distributions, we're going to call a Wasserstein gradient flow. And that's going to be kind of the optimal transport side of it. What we're going to find is that whenever you actually have the end, whenever you actually have that top layer, the end of it, if there's a proper amount of time that goes by, we're going to have some just kind of arbitrary measure of time, just a meaningful amount of time goes by, what you're going to see is that these tokens are going to collapse. They are going to collapse into a degenerate state, or a set of degenerate states. And this is something that is just the findings of the paper. And this is what the mathematics shows. So the goal of this paper is twofold. On the first hand, in this paper, A Mathematical Perspective on Transformers, they offer a mathematical perspective. On the other point, where is it? They give promising research directions. And that's pretty cool. So part one, modeling, we are setting up our self-attention mechanism. We're not just going to have self-attention, and layer norm. We are also going to have the unnormalized, I think it is, unnormalized self-attention, USA, but really it's just the same thing as self-attention with a couple of twists. And so we are going to set that up in part one. Part two, clustering, we are going to be talking about, there's a couple of parameters that we have to talk about, but essentially in the long time horizon, we are going to find that the particles tend to cluster. That is going to be the solutions that we find. And then in part three, they give us the second part of what was up here, the two in the twofold, which are just things that, okay, this paper, if we look at the very top, we are on page 3 out of 53. That's a lot of pages. This is a long paper. So they don't try to answer everything because this is already a lot of work. So they, leave some questions as an exercise to the interested reader. And that leads us into part one, modeling. So let's begin there. Alright, so what we're going to do is we are going to talk about the transformer, the assumptions that we're going to make, and what we're going to cut from it, because we are going to cut feed forward as well as a couple other things. We're mainly focusing on self-attention and layer norm. And we are going to use these two things in order to build our interacting particle system. So what we are going to do is introduce a residual neural network, which is of course based on a neural network. A neural network is a network that approximates some function f that takes in some real number dimensionality and maps it to real number of another dimensionality. And then you're going to give it some data where here's going to be a specific datum of maybe your x sub I is a picture of a cat or a dog, and then your neural network is going to be applied to this image and is going to output a 0 or a 1. This specific piece of data is going to be sampled from the dataset n that you plug into the network. And you use that to train the network, but we're only dealing with trained networks here. We are not talking about training whatsoever in this paper. And so inside of that, we are going to have a residual neural network, where we are going to have your neural network, which is represented right here at layer xk plus 1 of L total layers, and you are going to add to it the residual stream. You're going to add to it the outputs of the previous layer. That way there is a highway of information going straight through, where that information exists as a pillar, and outside of that you are going to add the manipulations to that data that you would like to add, which is going to be the layer of your neural network. Here, the classic ResNets were convolutional neural networks, but we're going to apply that to transformers, of course. Here, our sigmoid function is going to be a Lipschitz function, which just means that the gradient is bounded. It can't be above or below some number. And let's see, it is going to... Oh, that's really about it. So what we're going to do in the next page is we are going to take these k layers, and we are going to turn that into smooth time. So what we're going to do is we're going to take this x of k, and this x of k, we're going to subtract it. So we have delta xk plus 1 minus xk is delta x between these layers. And then whenever we just take the limit of that, we can say that that is the derivative with respect to time, x dot of t, of course. And so x dot of t is going to be this wt, where this is just some value that you have. This is a second learnable thing that's included in ResNets. And then you have your classical neural network along this idea of smooth time. And that's how we're going to cast this neural network into an ODE, and we are going to use that in order to talk about a interacting particle system. So, of course, you're going to have your input. Your input are going to be tokens. Now, whenever you have your neural network, you are going to have your you're going to have your words, the quick brown fox. And from there, you are going to have your encoding, your tokenization. So you're going to tokenize it. Let's say you use like maybe byte pair encoding or one hot or whatever. It doesn't really matter. And then you're going to have your embedding vector. Your embedding vector is going to take it from your dimensionality of your vocabulary to the initial dimensionality of your neural network. And that is going to be RD. And we're going to have n of those samples, so n of these tokens or activations or embeddings or whatever you want to call them, and that is going to compose the initial conditions. That is going to be our prompt. So we are going to have a layer norm between every layer, like the icing between layers of a cake. And so whenever you have it, you have your embedding layer. As far as I remember, I might make mistakes, I'm doing this off the dome, but you're going to have your embedding, then you're going to have layer norm, self-attention, layer norm, MLP, layer norm. Of course, we are cutting out the MLP entirely, so it would just be self-attention, layer norm, or layer norm, self-attention, layer norm is what I mean to say. And that layer norm is going to be a learned diagonal matrix. And what we're going to say is, wow, we trained ours and we got a identity. We got the identity matrix. That's crazy. So instead of just saying that we have a generalized time-varying axis-aligned ellipsoid, acting upon that is represented by the network because of the application of layer norm, we say that what we have is a unit sphere. We have this hypersphere that we're going to be using throughout everything. We're going to show that throughout the paper, we're going to show that whenever you have this initial distribution of particles, where the particles are, of course, the initial distribution of tokens upon this unit hypersphere, all of the particles are, generally speaking, going to collapse into a degenerate state or a small number of degenerate states. We're going to show through this Albert that this is not a terrible thing, and this is something that you kind of see in practice. And we are going to introduce the idea of the transformer right here in 2.3. So we have our initial conditions, which is the prompt that we are feeding in, and through all of the layers of the neural network, we are going to see that there's going to be some transformation of the particles. That transformation is going to be given by the self-attention mechanism. Here is the gradient, here is the particles and how they move with respect to time, and we are going to have this projection matrix. This is going to be our layer norm right here, and this is what casts it onto the unit hypersphere. So we have just looking right below, the projection onto x perpendicular of y, or acting on y, I should say, is just the tangent space. So this is going to be the tangent. Do you call it a plane? It's not necessarily a plane, it's just like n-dimensional. I guess tangent space is the best way to put it. And so we have the layer norm, and then we are going to have the attention mechanism. So of course the attention mechanism is QK softmax V, and so what we can see is up here we have this thing right here, which is going to be representative of the softmax, and we have Q times x sub I, where x sub I is the particle that we're giving self-attention to. It is going to attend to all of the other tokens, or all of the other particles, I should say. And we are summing over j particles, and here is that j right here, and here is the query times the input, and k times the other particles that we have in the context, or in the prompt, and there is going to be the inner product between those things. And that is going to be the inside of our softmax. Then we take the exponent. This beta is going to be our inverse temperature, and we have our partition function. And that is going to be this, which is just all the other possibilities. It's just basically turning it into a probability distribution of the prediction for the next token, of course, scaled by the values times xj, where j is, of course, the other thing that we are summing over. It's giving it a weight. And we're going to be talking about I as just a member of the particles that we plug in. We're going to say that the entire vocabulary is just the things that we plug in. It's going to be this n dimensionality. So we're kind of simplifying a lot of things, but just pretend like the embedding, just you get to hand wave it all away. And t is always positive time. And here it says that, of course, QKV is a query key and value, beta is the inverse temperature, and we have our attention right here, where they define this A, but we're never really going to see this again, so there you go. And what we're going to do on top of that is we are going to simplify this. We are going to give a simplified scenario where we train our QKV matrices, and they're all constant, and they're all equal to the identity, which is great. So we have our gradient here that is going to talk about how these particles are going to evolve with respect to time, can be given by this projection matrix, our layer norm, as well as our Q and K, but those are just identities, so they fall away. And then this is going to be softmax, and then we have our V, but that's going to be identity too, so they just fall away. And here is the actual thing that we're going to be using for self-attention. You can see it here, self-attention. And here's the partition function that follows from the exact same thing. And we are going to, we're going to talk about Albert. So whenever we talk about the particles falling into a degenerate state, essentially what we're saying is that the inner product between those things is going to be 1 because they are occupying the same space, or at least something approximate to 1, where in a histogram it's represented by 1. And what we see is that as time increases, or as the layer increases equivalently on this Albert, we see that at 1, at the activation 1, or I'm sorry, the inner product of these activations, we are going to see it increasing at them showing the degenerate state of the inner product being 1. And this increases and increases and increases, and as you get to layer 46, 47, 48, they are all occupying the same space, which means that these are all going to be in the same point in this latent space. Whenever you take your unembedding vector, that means that all of these particles are going to be contributing to predicting the same output. These are all just associated with a location in the latent space, a singular degenerate location. For remark 2.1, we are going to say that these have a strong resemblance to the literature of nonlinear systems, and that these also show a collapse. This is going to be similar to the Kuramoto model, as well as the Krauss model. Here is the Krauss model right here, and for the Kuramoto model, I pulled up just the Wikipedia page, and we can watch this. It tries to make noise, but we are going to turn that off. And we initially have these metronomes, which are going to represent our particles based on their phase, and Right now, they're completely independent. There's nothing funny going on here. But whenever we couple the systems by putting them on top of this can, there we go, and it's now coupled, there's going to be all of these things exerting forces left and right. There's going to be constructive and destructive interference, and those things are going to slowly add up and do little tiny momentum changes on these metronomes. And so whenever we actually go forward into time, we see that they fall into a degenerate state, or at least something close to it, because they were independent, but now that we added these soda cans, we coupled the system. And the coupled system, as time increases, falls into this degenerate state. We're talking about phases for degeneracy here, and particles in our paper. Jumping back to that. We see it going on with that. It says that none of these dynamics are contain parameters appearing within the nonlinearity as in self-attention, whilst set on the sphere. So that is kind of our contribution. I say our. I had nothing to do with this paper. I'm just making a YouTube video. So for remark 2.2, for permutation equivariance, we say that a function is permutation equivariant if it has some constant or some thing that you can pull out of this pi. If you can pull this pi out, then you can say it is permutation equivariant. Or, in other words, you can say that whenever you have some input x, if you modify all the inputs x the same way, then the output f of x is permuted in the same way. And given positive time, we are going to say that the transformer is permutation equivariant. So towards the complete transformer, here we're going to talk about the things that we cut. So we are going to cut multi-headed attention. You could have it to where your QK is going to be pretty big. Your QKVs. The entire self-attention mechanism could be replicated over some number of heads. Maybe you cut up the latent space, maybe you don't, doesn't really matter, because we are not going to use this whatsoever. We are also not going to use any feed-forward layers. You see that you have the heads here, the self-attention here, and then you have this, the MLP. We are not going to be talking about the MLP whatsoever. We're also not going to use any positional encoding, but I think we say that below. And that takes us to section 3. So what have we done so far? 2 seconds ago, what we did was we found out that we can talk about self-attention as a particle system on a hypersphere. And so we took our tokens and we planted them on, and then there's going to be some dynamics. Here, what we're going to do is we're going to talk about, okay, what happens to those particles? And what we're going to say in this section is that we can think of the flow of the particles. We can think of them as a Wasserstein gradient flow. Let's see, it is down here, I think. Yeah, the Wasserstein gradient flow. So we are going to talk about all of the particles. We're going to use a tool called a empirical measure, and we are going to build up a vector field from that. We're going to build up an energy, and then we're going to show that the particle movement can be thought of as a Wasserstein gradient flow for the energy. And that's going to be the main thing. We're also going to show that the equation that you get for this gradient flow is going to be an aggregation function. So not only are we going to be able to use very familiar and well-studied mathematical tools of optimal transport to talk about the self-attention mechanism, but we're also going to be able to say, okay, because it's also an aggregation function, we know that as time approaches infinity, it's going to collapse to a single point. And that's really important. So we're going to get through this, we're going to show that, and this is going to be a longer section, but this is a really, really important one. So let's start at the beginning, right here, at 3.1. I said at the beginning, I just summed up essentially what this says with what I just said. So there's the continuity equation. And so we just defined self-attention as the ODE, as x dot. And so now what we can say is, okay, so before we had all of the particles coming together and interacting with each other. But what if we change that? What if we twist it just a little bit so that we actually say, okay, now all of the particles instantiate a field, and that field is going to be what interacts with the particle. The movement of the particle is the field being applied to the particle. And we are going to say that all of the particles being placed onto the situation, onto the hypersphere, are going to be thought of as this thing, mu, which is a function of time and your input argument, which is going to be our particles. This has the name of the empirical measure, and it's going to be this thing right here, to where essentially we're saying, okay, so imagine that you have just the quick brown fox, 4 different tokens, and you put them onto the hypersphere. They're going to evolve in some way. And so we can think of it as 4 tokens, and those 4 tokens are going to start somewhere, and they're going to flow, and then they're going to end somewhere. But you could also say, okay, so what if we said that the quick brown fox, for each token, instead we give it 2 particles. So now, instead of having the 4 particles, we set n is equal to, instead of 4, now it's doubled to 8. And each point is going to be some place to where we superimpose each number of particles, whatever number we want, on the actual particles that we have, and it's going to be a delta Dirac. There's just a delta Dirac for that thing. So we can integrate over the entire space, which is equivalent to integrating over this empirical measure. And the empirical measure is where the tokens are. So you can say you have 8, or maybe you have 4 tokens on each place, or maybe 20, or maybe 1,000,000, or maybe you take the limit as n tends to infinity, and you say that you have those 4 initial starting positions. That way, the mass can evolve smoothly, and subsections of each token can flow wherever they need to go. And that's one way of dividing and conquering this method in order to figure out the dynamics of where the particles want to evolve in this latent space that is the hypersphere. So we're going to use this, and as you can see, this empirical measure is going to be what drives the actual vector field. So the empirical measure, the particles that we actually see in practice being planted onto the hypersphere, are going to instantiate some vector field, and that vector field is going to be applied to each particle, giving us the movements of each particle, the gradients of each particle, or should I say time derivative. And that is essentially what we have. And here we just map out the exact same thing. This is our very familiar self-attention, but now we're talking about self-attention with respect to a vector field. And that's really cool. And from there, we're allowed to talk about our continuity equation. Our partition function is unchanged. And so the continuity equation essentially is the preservation of mass. And so these are actually going to be probability distribution functions. And the reason for this is because whenever we think of the transformer, what it's actually doing, the transformer is not predicting the next token that comes in a sequence. The transformer is actually predicting the probability distribution of the next token to come. And so whenever we actually talk about each point in a latent space, there's going to be some associated probability mass with that. Every output of the latent space, every point in the latent space, is going to be a distribution of the probabilities of tokens. This is just a fact of transformers. We are going to introduce the continuity equation for this probability mass, which essentially just says that, okay, so if you have some probability mass flowing out or in from a point, it has to come from somewhere. You cannot teleport probability mass anywhere. We are going to start by putting all of these pieces, all of these particles onto the hypersphere, and then they have to move in some coherent way. There has to be some flow. You can't just pick one up and put it on the other side. And so we can see that here. We have the vector field applied to the empirical measure, the vector field applied to the set of particles that we actually see. The divergence of that, or should I say the flow, is a maybe good way to put it here. And the flowing of all of these particles is going to be equal to the negative of the time evolution, of the empirical measure, of the particles that we actually see. And of course, the initial conditions are the initial conditions. And so that's how we're going to set up this continuity equation to make sure there's no funny stuff going on. Furthermore, while talking about no funny stuff, we are going to say that everything we're doing is well posed. We are going to use a Borel probability measure on the surface of this sphere. We are going to only use good initial conditions, and we're going to make sure that nothing too crazy goes on. We're going to talk about positional encoding right here, and I'm not joking, nowhere else. This won't come up again. But technically, there is this other thing that we do before we actually take our tokens and throw them onto the hypersphere. So of course, you take your tokens, use byte pair encoding or whatever your favorite thing is, and then you pass it through the encoding vector, which just takes it from the dimensionality of the vocabulary to the dimensionality of the transformer. Now, after you do that, and before you actually plug it into the transformer, you see the transformer, of course, as we're all familiar, the transformer works on sets. The transformer doesn't care about the order of things going in. But in a sentence, we actually do care about the order. So in the Vaswani paper, what they do is they introduce a set of sines and cosines that they add in after the weight encoding, so that there is some kind of information put just literally summed onto this weight, this encoded weight, saying, okay, so this is where it's coming from. And the sines and cosines give it some kind of information that the transformer can take and say, okay, because of this information that was literally just summed on top of this, I can tell where each element came from. I know the positioning of each element in the sentence. So I know the quick brown fox, instead of just a bag of words. So that's the thing that's added on. That's going to be kind of important whenever we're thinking about this thing like holistically, but not so important whenever we're thinking about the hypersphere. Here is going to be the mean field limit. This is going to be what I was talking about just a second ago with taking the number of particles from 4, the quick brown fox, and taking the limit as n is 4 tends to infinity. What we're going to say, the more technical thing, is that we're going to have some Wasserstein 1 distance. And so we are going to have this case here, where there is some finite number of particles, the quick brown fox, and here is going to be the infinite number of particles. And so the distance between those two things is going to be 0. We are only taking initial conditions where this is true. This is the only thing we're thinking about. Of course, here in this paper, we're not doing any weird empirical stuff. We're not doing any experiments. This is pretty theoretical, so we can just say that's what we do. And so we have de Bruchen's argument, because these are only for the initial conditions. This argument is that the time evolution of these things, the Wasserstein distance between these two measures for the finite and the infinite case, is going to be some constant times what we declared to be 0. So 0. And that's pretty cool. So this means that we can take this mean field limit. We can take the limit as n tends to infinity, and there's really no issues there. We're not doing anything too fancy. And I don't think this adds anything too meaningful. And then we're going to have the interaction energy. We are going to introduce the actual energy, the interaction energy of the particles. What we want is our x dot, our self-attention, we want that to be the Wasserstein gradient flow. What is it the Wasserstein gradient flow of? Why, of the energy. We are going to build up this energy. And the energy is going to be extremely familiar. It is going to be the double integral, and essentially it is the self-attention and then the reversed self-attention. So it is going to be particle x and its energy with x comma, x apostrophe, x prime. That's the word I'm looking for. So it is going to be x and x prime, and then the empirical measure of that particle, then the empirical measure, the same empirical measure of x prime. And so those two interacting with each other, and then that for every set of particles is going to sum together for the energy. So this is essentially saying, with some constant out front for normalization, that we have all the particles interacting with each other. The integral across that empirical measure is going to give us the energy. And the energy is, of course, going to be a functional on top of this empirical measure. The time derivative of this thing, which is going to be the first step towards building our Wasserstein gradient flow, is going to be, well, we just take the derivative, and that ends up being this thing here. And this thing here is saying that we have the vector field applied to the particle, the integral across the entire empirical measure. So we have this vector field, mag squared, multiplied by our partition function, and then just integrate it out. And that is going to be the time derivative of the energy. And we're going to solve this using integration by parts, and we know that z is constrained like this because the inner product can, we remember that it's an inner product, right? It has this kind of thing right here which maxes out at 1 or -1. And we chose for v to be equal to I. This right here talks about the difference, which we bring up in just a second. Oh, wait, no, not even just a second, right now, for proposition 3.4. So We have this thing right here that we want to essentially turn into what our Wasserstein gradient flow is. We have not shown that this is self-attention yet. That's going to be the kind of key phrase. That's the punchline of all of section 3. So let's just talk about what this energy kind of does. What happens whenever you maximize it? So you have all of your particles, they're going to be distributed on your hypersphere. What happens is you maximize the energy or minimize the energy. What's going to happen there? And so the unique global minimizer of E is going to be the uniform measure, essentially saying the particles are going to get as far away from each other as they possibly can. And the maximizer is going to be a Dirac mass centered at some x star. If I zoom, does that just with it? There we go. Cool, that kind of fixes it. Of course, I think that's ugly. Oh, that's fine. That's good enough. You have some black bars on the side. I'm going to ignore that. If you maximize the energy, then it's going to collapse to a single point. We're going to show that here whenever you maximize the energy, and we're going to see that in just a second whenever we actually figure out the form of our Wasserstein gradient flow, that it's an aggregation function. So we're going to see this kind of collapsing twice. This is the first time, if we want to maximize the energy. And the reason that this is happening is because we chose for our values to be this just literally ones across the board. And that makes the force attractive, just like you. But if we took the case that the values are negative, then we would have a repulsive force instead, and then the opposite would happen. We are only taking the case that we have V equals I sub D. That is the only thing that we're really going to focus on. This case here is going to be one part of section 9.1, where we kind of talk about in 9.1, like, okay, so what's a more realistic setup for the keys, queries, and values? Now, the idea that the global maximizer is a Dirac mass is easy to see. And that means that whenever we look at the energy, if we want to maximize this is the key thing here that we would change. We want to maximize this inner product, which means that we want this inner product to be, if it's orthonormal, or if it's normalized, I should say, not orthonormal. If it's normalized, this should be 1. If we maximize that, that means these two particles are the same. That means that they occupy the same position, and that means that we collapse to a single point. For the minimizer is a little bit more involved. So what we're going to do is we are going to introduce this f of t, and this is going to be the stand-in for the actual self-attention, and it's going to be e to the beta t, changing the energy to this right here. And so what we're going to do is we are going to do a ultraspherical, or Gegenbauer, polynomial expansion of f. Kind of like a Fourier transform. I've never dealt with this specifically, I've only dealt with the Legendre polynomials, but it seems to be the same idea, to where we have some set of orthonormal polynomials, and we are trying to understand the surface conditions of this hypersphere. Just like whenever we take the electron configuration on the surface of a hydrogen atom, it's going to be pretty much the same thing. And we are going to take the case to where lambda is equal to d minus 2 over 2. Now we had the requirement, I didn't highlight it, but I can right now. D is greater than or equal to 2. So we're going to take the case to where lambda is positive. And we are going to try to find, essentially, this thing wholesale. So what we want to prove is this thing wholesale. So we want to prove that this f hat that we define right here, and also right here. So inside of this, we want to show that the f hat is greater than 0 for all k is greater than 1. If we do that, then according to this thing, we prove proposition 3.4. And proposition 3.4 is that the minimizer of the energy is the uniform measure. So essentially, this is the thing that we want to prove in order to prove that we get the uniform distribution over the energy minimum. And in order to do that, we use the Rodriguez formula. So as we look at this f hat, we remember our gamma functions, and of course we remember that if we have a positive input to the gamma function, the output of that argument, or the output of that function, is going to be positive. So all of this that comes before the integral is positive, because this right here is greater than 0, and we're only concerned about this integral right here to make sure that this is going to be above 0 for all k. And so we know that f of t is going to be positive because of the way we defined it. And we know that this is going to be positive because of the way that we have defined the bounds of time. And so we are really just concerned about this c right here. So we use the Rodriguez formula to check out this c, and we find that everything is positive except for this little bit right here. This -1 is going to be kind of the important thing. And this is also going to be a little bit involved right here. This is also going to be the k. The kind of thing that drives the Rodriguez formula is that we are at the kth time derivative in order to define this set of orthonormal polynomials. And what we are going to remember is that this is linear. So we can literally just pull out the negative. So we can literally just pull that out, and then we integrate by parts k times. And so that integration by parts yields this thing right here. And so if this thing is positive, or if this thing holds these, spoiler alert, it works. So this thing is going to show that this last part here that we're wondering about is always going to be above 0, showing that this thing is above 0 for all k is greater than or equal to 1, and then showing that the energy minimization is going to be the uniform measure. And of course we do see that under this case, or it's 0. And that means that the integral overall is going to at least be, sometimes greater than 0. And that means that we satisfy this condition, and we did it. Go team. Cool. So that means that as you maximize the energy, you collapse to a single point. But as you minimize the energy, then you are going to spread out as much as possible. In some of the YouTube videos from the author, Rigolet, he talks about how he was really worried that he would have to do energy minimization here, because apparently for energy minimization, under more realistic circumstances, you would be dealing, instead of just the uniform measure, you would be dealing with the problem of sphere packing, which is apparently a really hard problem. But because we're just maximizing the energy, then we just have a total collapse to a single point, which really solves a lot of headaches. So we understand about how the energy is going to evolve. So let's talk about, finally, this Wasserstein gradient flow. So one issue that we're going to have, one big problem, is this logarithm right here. So we're actually going to kind of expand q equals k equals I, and v equals plus or minus I, and we are going to change it. We're going to change it to qk is equal to kq, which is equal to plus or minus v. And the problem, so that's just an aside, we do that. But then we see that this logarithm is right here. And that logarithm is the reason that this is not the gradient of the first variation of a functional, which is a requirement in order to have a Wasserstein gradient flow. So we introduce the proxy. How do we get rid of it? Well, there's two ways to get rid of it. One way to get rid of that logarithm is to augment the transformer itself. And if you augment the transformer to lose that thing, you get something that was already made. You get something called the sync former, which I think Yannick Kilcher made a video about. And they replace self-attention by a doubly stochastic self-attention using the Sinkhorn method. I think it's the Sinkhorn-Knopp algorithm or something like that. I don't really remember. But what we are going to do, so we're not going to do that. That is one way to do it. That's not what we're going to do. The second way is just to get rid of the partition function. If you just get rid of that, the logarithm goes away. So we replace that partition function with n. That's it. That's what we do. And we get this thing here. So we're not using a partition function, so we are not normalized, or we are unnormalized. And we get the unnormalized self-attention, USA. And so now we get this augmented x dot. But since we augmented the self-attention, we kind of have to rebuild a few things. So let's go ahead and do that. So let's rebuild the continuity equation with the unnormalized self-attention. It's going to look exactly like this. It looks extremely similar, but it no longer has the z in there. And of course, initial conditions are initial conditions. And as soon as we do this, we say that, okay, we did it. Now, this unnormalized self-attention is the Wasserstein gradient flow over the energy, which means that we unlock a lot of potential. There's a lot of mathematical tools that we can still use, and there's a lot of analysis that we can do. There's a lot of guarantees that we get. There's a lot of optimal transport we can do, and that means that we can do so much cool stuff. So let's just keep expanding on this. So let's talk about the interaction energy, which is of course going to be taking the projection on the sphere and just mapping it to a number. So we have the vector field, which is defined right here. And what we're going to say is that, well, what we want to show is that it satisfies this thing. That this is, oh, I scrolled up one. That this thing right here is this vector field. Instead of saying we have these particles, we're going to say this vector field is going to be the Wasserstein gradient flow, the gradient of the first variation, which I've highlighted right here. Oh, it says it also right here. The first variation of the energy. And that is this is the Wasserstein gradient flow. Now, this vector field that we created before is the thing that we want. Of course, if you've been paying attention, it says autocalculus like 15 million times. That is going to be essentially the set of tools that we use in order to make everything work. It is just the set of tools that makes everything function, which is really cool. I'm going to read this paper soon. I might make a video about it. Let's see. I don't know. So this is totally it. Oh, I said we have to prove it. I guess we already have it, and that's great. So what we're going to do now is just reframe this. So this is totally valid, but you can also rewrite it if you want. You just take this this functional stance instead of two functions acting on each other, as we have right here. You can say f on g, acting on x instead, and that gives you this energy right here, which gives you this function here. This is the exact same thing, just written differently. And now, before, totally valid, we had this continuity equation, but this was talking about the particles, and maybe we want to talk about it with respect to the vector field. So we can rewrite the continuity equation with respect to the vector field, and that is a pretty cool thing, because it reminds us of a few other things. So this allows us to consider the Lyapunov identity, where that just means that we have stability as time goes on. It's some kind of proofs about stability, some kind of guarantees. And we are going to also be able to show, with this lemma, we're going to be able to show that the time derivative of the energy given our metric is going to be this thing, which is very reminiscent of what we saw earlier, to where we have the gradient flow mag squared, and for positive t. And this thing right here is the familiar thing that gives us the aggregation equation. This specific form of a Wasserstein gradient flow is this 3.10? No, this thing right here. This continuity equation. But this thing also, which comes out of the continuity equation, is an aggregation function, which means that there is going to be clustering. There's going to be a strong clustering in the particles given infinite time, or something close to that, is going to collapse to a single point. Now, it's kind of interesting. There have been a lot of papers showing this, and there's also a lot of talks by the authors where they kind of say, like, oh, it looks like the time is something that the network just has to learn on the fly. This concept of how long should we go? Whenever you actually have your... so here we have some smooth time. We have continuous time because we changed it to a neural ODE. But the actual transformer does work in layers. So the transformer itself is going to have to understand how much of this time to skip, how much time happens inside of a layer. How close should you get towards this total collapse of particles into one cluster? And so that's a really interesting thing that I think is just an open area of research. And that's pretty cool. What's also pretty cool is talking about particles. So right here we have the vector field recognition of the Wasserstein gradient flow. But let's just talk about the particles for just a second. Let's kind of sketch this out. So we can rewrite the energy as this thing right here. It's the exact same thing, just slightly different. Now we have the unnormalized self-attention instead of before having the normalized self-attention. Whenever you do that, it shows you that your x dot now changes slightly to where you have this gradient. This gradient is defined right here, where d sub I is acting on the ith particle, where the particles are shown here. And whenever you actually map this out, if we remember, unnormalized self-attention is literally x dot. Whenever you calculate the gradient of this with respect to each particle, you get that the unnormalized self-attention is just n times that thing. And the ith derivative of the energy acting on this set of particles, big X, is going to be normalizing constant, sum over all the particles, projection matrix, self-attention, and it is going to be the exact same thing except 1 over n. So we're just going to slap an n in there, and now this thing is going to be, this derivative here is going to be pretty much the same thing as our unnormalized self-attention. It's just off by 1n. And that is going to, of course, yield our thing right here, where this is our Wasserstein gradient flow for the unnormalized self-attention. This is going to be its form. And that is essentially what we want to show. Well, not the only thing. We want to show it for self-attention. So, okay, so we have the logarithm. And the logarithm comes from the partition function. So how do we solve that problem? How do we actually figure out if self-attention is going to be the Wasserstein gradient flow instead of our proxy, the unnormalized self-attention? Well, the answer is, why don't we just take that partition function and instead define the space as something that eats the partition function instead of the self-attention eating that partition function. So we are going to have a modified metric. We are going to change the definition of a dot product. So before we had this thing here, the dot product between two vectors, the inner product I should say, is literally just this. But instead, what we're going to do is we are just going to slap this thing in here. We're just going to slap the z in there, and that's just how we define the inner product. Congratulations, there you go. And that's how we're going to solve the problem in order to show that self-attention is a Wasserstein gradient flow, but it's a Wasserstein gradient flow of a modified metric. We're just moving the space between particles. We're moving the space between points, I should say, not between particles. We are going to take this definition of values, quies and carries. Yeah, I'm sticking with that. Quies and carries. So whenever we do that, that means that in the self-attention, we can just slap a v right here, and that just makes it work out. That's pretty cool. And so we can rewrite, well, not rewrite, we can just define these things here. That way, whenever we actually get the full self-attention, we can write it as this. But we need to show this. We now show that this is actually a valid thing to do, that this is the Wasserstein gradient flow of our modified metric. And now we are just redefining our gradient as a thing that is calculated with respect to our custom metric, our modified metric, which is going to satisfy this thing. So instead of having the vector field that we classically had, now we have the flow associated with some vector field y, this modification on the space, I suppose, that is going to affect this b. And this b right here is going to be our classical self-attention. So we need to show that. We need to show that this thing is a valid thing to do that works on the tangent space of the surface of the hypersphere. And by linearity, we only have to show that it really works on the first particle, because if it works on the first particle, it's going to work on all of the particles. Then we're good to go. So we're going to define this y to where it works only on the first particle. It only modifies that thing. The rest are set to 0. Solving that ODE, we of course get this solution, and this is going to be the flow of the flow associated with vector field y. And so now we just plug that in, and whenever we plug that in, we get this thing here, and this whenever we plug in this thing here, we can say that it applies to all of the other particles because of the way that we have defined projection, and if we assume that these things here are symmetric. So now we get this thing here. As we plug it back in, these two things are equal as desired. And so that solves that. But we also want to solve this for the case of measures. We also want to solve this for the continuity equation. And so what we want to do is redefine the continuity equation, which we did just a second ago for the unnormalized self-attention, but now we want to do it for regular self-attention within this modified metric. So we should be able to write that this thing actually holds. This is going to be our continuity equation. and we are going to define the first variation of the energy to specifically be this integral right here. We're going to focus on the continuous case, and we're going to have some fixed metric, projection AC, on the surface of the sphere, and this is going to be similar to the well-known formal Riemannian reinterpretation of the Wasserstein space using autocalculus. Once again, we see autocalculus. So we're going to see this thing here, which has a great name, and this thing is going to be on the closure, the L2 closure of the metric, the gradient of some arbitrary waveform will be the waveform that's a member of the Cauchy solutions on the surface of the sphere. And the metric tensor that we have for the inner product. So here's the classical inner product. This is just whenever you usually do it, this is the inner product that you get. And so the gradient flow of some arbitrary waveform is going to be defined as the integral over the metric of the inner product of these waveforms, but instead we endow it with. Instead, we are going to add in the first variation of the energy. This modification of the space of the gradient of these waveforms is going to allow us to redefine our metric and show that our self-attention is a valid Wasserstein gradient flow. So we show that this thing absolutely holds. This is the vector field mag squared given some metric and some energy, derivative with respect to time from 0 to 1, between these two things here, between our empirical measure and some vector field, or I should say just some vector. I don't think it's necessarily even a field, it's just vector v of t, satisfies this thing down here, where this is extremely similar to the continuity equation, but now it's two things together. It is this vector times our empirical measure, where I really interpret this thing to be very similar to gamma in relativity, if that helps anybody. And of course, initial conditions will be initial conditions. And so this is going to be a generalization of the celebrated, this is a great name, Benamo-Brenier formula, which we are going to dub this weighted Wasserstein distance W2 sub 2 EB, acting on two metrics right here. And so we are going to say that this this weighted Wasserstein gradient is going to be shown by this W right here, W sub EB, W sub E sub beta. And this thing right here is going to be essentially the Wasserstein gradient flow. And that thing, inner product with this thing, given this constraint for the space, is going to give us this derivative right here. And so we should be able to satisfy this. If we satisfy this, then this thing right here is the valid Wasserstein gradient flow. Or the weighted one, I should say. And so what we do is we literally take this, and we just take the definition that we had for the first variation and plug it in. And so we have this here. Now, whenever we have this, we want to show this thing right here, so we need to break it into an inner product. So this right here is literally this, like it is the same thing. And then that is equal to this inner product right here, which is equal to this thing here. So now this here is equal to this inner product, and this thing in the middle is going to be the same as this thing in the middle. That means that this is our valid Wasserstein gradient flow, as desired. So what we can say is this is the end of the section. This is where we are. The self-attention that we just introduced, the self-attention that we had, is going to be a Wasserstein gradient flow, but not a normal one. We have to modify the space. We are going to have a weighed Wasserstein distance in order to talk about the movements of the particles, in order to talk about the evolution of the particles based on the energy that we have defined so far. And that is the core of what we're doing. After this, we move on to part 2. So we know that this is an aggregation function, and so it is going to collapse. We're going to start talking about that collapse, about what it looks like, especially with respect to beta. The next section is going to be small beta, and then I think it's like large beta. I think those are the only two. I don't remember. We're literally going to see it in several seconds if you keep watching this video. And so this is the big idea, to where self-attention is a Wasserstein gradient flow, and it's an aggregation function, so it's going to collapse. That's kind of the important takeaway here. But let's keep moving on. Alright, so for this section, what we're going to be talking about is when do we cluster? And so if we look at figure 2 real quick, the green parts are where we cluster. And if you look very closely, it's almost all green. You're almost always allowed to say that you are going to collapse to a single particle. You can see here, it's only dimension 2 that you have some caveats, and that's not even always. You're almost always guaranteed to have a collapse to a single cluster as t tends to infinity. So the first section, oh, there's some text here. We're gonna skim right past it. The first section is whenever we're dealing with small beta, and then section 5 is going to be for large beta. And so essentially, we're going to ask ourselves, okay, so we are going to cluster. How is beta going to affect whether or not we cluster? And so what we can ask for small beta is, what is the smallest beta that we can take? And the answer is, of course, 0. Now, whenever we actually plug that into SA or USA, we find that it's essentially just center of mass. It's not quite, it's the projection of the particles, so there might be some funny stuff, but essentially it's just like you sum up all of the particles and then you divide by the number of particles. And that's where you are collapsing to. Those are the dynamics of each particle. And so this is pretty much a guarantee with this, and this is what we're going to be working off of. So let me say a few things before we jump into 4.2. So we are just going to narrow this down a little bit, and we are going to say that, okay, so theorem 4.1 says essentially this: if beta is 0, you are collapsing to a single point. And we are going to say for Lebesgue almost any initial sequence, where this means that I'm pretty sure the Lebesgue measure means that you have a metric that can be high dimensional. And almost any initial sequence means for any good random sequence. For example, a good random sequence whenever you're flipping a coin like heads or tails is that it either lands on heads or tails. A bad random sequence is you flip the coin and it lands very perfectly, completely straight up, and you get neither heads nor tails. That's not very realistic. That's not very likely to happen if you're actually flipping coins. So you can also take it for the sphere. They bring it up right up here with the antipodal configuration. You can also think of, like, you have your sphere, let's say just in 3 dimensions, just for fun, and you can put all of your particles right on the very, very top, except for one singular particle. You can put one particle directly on the bottom, and this is going to make a saddle point. This is going to make a point to where the particle on the very bottom is going to be stable. It's actually not going to collapse to a single point. Everything is going to stay like it is, and then you found equilibrium. But that's not going to satisfy the almost any initial sequence, because that's not a very likely random situation. So we're going to kind of toss that one out. And other things like it, of course. So this is how we're going to write the initial conditions, to where we have the particles at time 0, where we have some x sub I, and I is a member of n, and n is the set of particles on the surface of the hypersphere, as we're familiar with. X star is where we collapse to, and there's going to be some unique solution to the Cauchy problem that satisfies, oh, here we can see it's time dependent because of this little argument dot, and we see that the limit as time tends to infinity of each particle is that each particle tends to x star. The location of the particle with respect to time tends to x star, for any I is a member of the set n. This is going to be our consensus behavior, and we are going to jump into the kind of interesting thing, the case where beta is much less than 1. Now, what we're going to do is we're going to say, okay, we have the exact same thing. This thing highlighted right here is the beta equals 0 case, and what we're going to do is have some perturbation on top of this beta equals 0 case, where it's going to change by order beta. And so what we're going to do is kind of analyze this order beta to see, okay, so how big is this thing? Can this completely throw us off? Can this change everything so that we end up actually not clustering to a single point? So we're going to investigate it a little bit with theorem 4.2, and I think 4.3, we'll get there. So what we're going to do is say that we have a dimensionality of at least 2. And so for some beta equal to or above 0, we are going to say that you're going to have some subset of beta that is a member of the initial sequence of particles on the surface of the sphere, or this hypersphere, and these are going to be the ones to where as time tends to infinity, then the probability as beta tends to 0, the probability of being in this subset tends to 1. which says that, okay, so you have some beta, and this beta is just positive. So let's just call it like 100 billion or something like that. As it tends to 0, you get more and more probable that you are going to fall into the subset where this Cauchy problem has the solution that it collapses to a single point. Q and K don't matter here. The only thing that matters is that we have an attractive force, and we are going to introduce a little bit more vocabulary. So we're going to introduce alpha clustering, which says that, okay, so just take 2 particles, and this needs to hold for all particle pairs inside of your set N. The inner product between 2 particles needs to be bigger than A. So like it needs to be like a more acute than this alpha right here. And we are going to say it is alpha clustered if this alpha is greater than 0, essentially like if they're all on the same hemisphere. This ends up not mattering so much because we're going to show that everything is going to fall into it. It actually doesn't matter so much if they're on the same hemisphere. And also, we're going to show that all particles are guaranteed to be on the same hemisphere. So both angles of that are actually solved. We're going to show the hemisphere thing in like section 6, which will be in just a second. And so we are also going to introduce the critical time m. And so m is going to be whenever you just imagine that you have all of your particles so far and they're just distributed across the sphere. Whenever we have beta equals 0, which we're going to show off by this little 0 here down below, and we're also going to show off beta equals 0 in the upstairs with the x. So we know that whenever beta equals 0, it's going to collapse to a single point. So that means that if they're not all the same, or on the same hemisphere, if they are not alpha clustered above some 0, just wait. Just give it some time, and they eventually will. And so we're going to say that critical time m is whenever it goes from this does not hold to this does hold. And of course you can choose any alpha for some arbitrary m. And so here we're going to choose 3/4, which I think if you're in 2D, that means it's like 40 degrees or something like that. It's kind of an arbitrary number. We just kind of choose it to describe this example. So we're going to say that for any pair, each pair is in the set is going to be greater than this 3/4. And as soon as you hit this, then we have hit critical time m. And so we are going to define this as the subset of beta equals 0 with critical time m, which is a member of the subset of betas equal to 0, which is pretty straightforward. And we're going to say that this is an open set. So the open set essentially just says, okay, so once you hit m, all of the m plus 1s are going to be members of this initial set. Like, you're only going to become more tightly clustered as you collapse to a single point. So these values are going to grow and grow and grow and grow, so you're more guaranteed to be alpha clustered. So we're going to show that this is an open set, and this is going to be important for this next thing that we're going to show just down here. And so we're going to be able from this to say, okay, so this looks really similar, except instead of t going to infinity, now we have this critical m going to infinity. And instead of up here, we had just this general subset with the subscript beta, now we have s sub 0 upstairs at the critical time m. The probability of being in this set as m tends to infinity, as time increases, tends to 1. You are almost guaranteed to be in this set as time goes on. Now, we have that, and what we're going to do is use the Duhamel formula, where this essentially asks, like, okay, so the perturbation, what is the scale of the perturbation that we actually have? Now we're kind of asking ourselves some questions about this order beta term. So how big can it be? And so that's what we use the Duhamel formula for. It measures the actual size of perturbations. Here you can see this x sub I with the superscript b, and here we can see, or I keep saying b, it's a beta. It's been a beta the whole time. There's no b's, but I'm going to keep saying that because it makes me happy. And here we have the superscript 0. So it's just asking, okay, so like that beta term, how big is that going to be, the order beta? And we get, using the Duhamel formula, that we get this thing right here. And then what we're going to do is employ Gronwall. And Gronwall essentially asks, okay, so you have this thing that has a certain size. How is it going to evolve with respect to time? How much is it going to be able to grow? And somehow you get a 3 out of this. I'm not quite sure how, but this essentially says that it's only allowed to grow with size respect to itself. So it's only able to grow proportionately to itself. So there is some exponential bound with the scale of which it's able to start to grow. And so we get this thing right here that tells us how it's going to change with respect to time. And as you can see, this has a beta and this has a 0. This is going to be important as we actually switch to betas in the term instead of the inner products being zeros right here with beta equals 0. We're interested in that beta term and seeing how it evolves things to see if we're still alpha clustered with a positive beta. Let's see, once we employ that, we actually get this term, which tells us, okay, so here's the actual difference. Here's how it scales with respect to time for that order beta term. And whenever we actually plug this in due to 4.4 to figure out exactly how this beta term is going to change with respect to our m instead, we get this thing here because of our guarantees from alpha clustering. And we can also plug in, we're going to combine 4.2 and 4.5 in order to get this beta term for alpha clustering based on the 3/4 that we actually plugged in and some beta. This is for it to just be half clustered. These numbers seem to be more or less kind of arbitrary, but hey, pick your favorite numbers. And so the inner product here, the main difference, like I said just a second before, is that we actually have the betas here, which we're allowed to do because we actually pulled this thing out here. And it says also, oh, right here. It said it above, but it also says it right here, that we employ lemma 6.4 in order to guarantee that this thing holds. Lemma 6.4 is essentially an extension of this, except we pretend that there's a beta right here as well. So it's for any beta, and it says essentially that this order beta is going to just be a constant, and this 3 right here is a separate constant. So there's just going to be some bounds on the actual upper limit of how much it's allowed to vary from the just from any initial case. And that is pretty much how we show that, all right, so we had the betas equal to 0. Whenever we have that, we're guaranteed to cluster down to a single point. And we also showed, with what we just went through right here, that we are alpha clustered. And because we are guaranteed to be alpha clustered at this time t equals m, that means that we are guaranteed for the set of any small beta to tend to a singular cluster. And so that means that if beta is equal to 0, it falls to a singular cluster. If we have some small beta, it's guaranteed to fall to a singular cluster. And the next question is I'm sorry. There's also theorem 4.3, which I'm not going to get too deep into. It essentially just says that there's some beta there's some c for which this thing actually holds. And if this thing actually holds, then you fall into a singular point. The reason I will not be going too deep into it is because it says that you can just throw it into Appendix C. And that leads us into Section 5, which is apparently about the same. It's about the same proof, except it's just for if you actually have a large beta. And as you can see, for small beta, beta is going to be less than c inverse n, but over here we go from inverse n to n squared. And so those are going to be two proofs that are actually thrown into the appendices, so I will not be going over them. But it just shows that, okay, so for the beta, it doesn't matter what beta is, you are going to collapse to a single point if you're working off of this idea of perturbations. And that essentially sums up those two sections. I'm kind of flying through these because 6 is actually the interesting thing, in my opinion, for the high-dimensional case. Alright, section 6. So we will now elucidate the role that dimension D plays in clustering results. So whenever we had section 4 and 5, essentially we were saying, okay, so as long as beta follows these specific things, then we can show that we collapse down to that singular point. Here we're actually going to be able to relax that. And this is kind of interesting. So they were made aware of theorem 6.1 after the first version of this manuscript was actually pushed out. It was in CRMB24 that they showed that if you're in d is greater than 2, one can move all particles in the same direction. And this little change allows you to say, okay, as long as d is greater than or equal to 3, you only have to say beta is non-negative. That's the only thing you have to say. Then the rest of this is going to hold. So let's jump in and actually talk about this. So for the first thing, we're going to have remark 6.2 for invariant measures. In the theory of dynamical systems, it's often the first question to find smooth invariant measures. But we're essentially taking all of the particles and collapsing them down to a single point. So there's not going to be really good preservation of volume or anything in those means, because a lot of the dimensions are just going to become just not used, where everything is just falling down to a singular thing. So we are not going to have a smooth invariant measure. That's just not really going to exist. So we move on. 6.1, clustering at an exponential rate whenever d is greater than or equal to n. Oh, so this section. Let's talk about this section. Essentially, what we're going to show is that as long as you have that d is greater than 3 and beta is non-negative, we're not only going to be able to say that you are going to collapse down to the singular point, we're also going to be able to say that you do this at an exponential rate. This is the key takeaway, that you are not just saying that you are clustering, we can also talk about the speed at which you cluster. And that's really cool. We're going to talk about open hemispheres at first. We're just going to assume a couple of things. Let's break through theorem 6.3 and get to those assumptions. So what we're saying here is that you have n is greater than or equal to 1, and beta is going to be greater than 0, and suppose that the dimensionality is higher than the number of particles. And you have some initial conditions that we are now quite familiar with. The initial sequence of points distributed uniformly at random almost surely gives you some x star on the surface of the sphere and some constants such that we are going to get this familiar thing, where the difference between one specific particle as well as the point at which all particles are going to collapse to is less than or equal to this exponential thing that is tending to 0 as time tends to infinity. In fact, Q and K don't even matter here. They can just be anything. The only important thing is that V is equal to identity. So we just have positive interactions everywhere. So what we're going to introduce is this idea of W. And W is going to be asking, are you on this open hemisphere? Do you see? So for all initial particles, we're just going to say this for initial particles at first, then extend this. So the inner product of W and any particle, whenever it first starts, is going to be greater than 0, showing that it is on an open hemisphere. So this is going to lead us directly into lemma 6.4. Is it lemma 6.4? Yes, it is lemma 6.4. And so this is going to be extremely similar to theorem 6.3, but the only difference is right here it says almost surely there exists some x star, but here it says there does exist some x star. And the reason that we can say that it exists is because here we just set it up so the initial conditions just satisfy this W. Before we say, okay, probably you're on an open hemisphere. Here, you're probably on an open hemisphere. Here we say, okay, we're just going to design it so that you are absolutely on an open hemisphere. And this is going to be what we're working with for a minute. We're going to come back to the idea of working with the probability of being on an open hemisphere. But for now, we're just going to assume that your inner product with W is going to be greater than 0. We're going to assume this for quite a while. So Q and K still don't matter. They could be anything. And so for remark 6.5, this is a bit of a spoiler because we're introducing x bar before we define x bar, but every particle is going to be going to some point. over infinite time, that point is going to end up being the cluster. Every point is going to end up going to that same point that we call x star, but we're not guaranteed that to begin with. So we're going to say that at least every point is going towards something. Every particle is going towards some point, and that point that every particle is going towards is x bar. We'll go over this in good detail. This is a bit of a spoiler. We're saying that whenever you do have this thing that we will eventually show, this thing is Lyapunov asymptotically stable as a set, and in fact, it's exponentially stable. This is also going to come back to Kuramoto models, which we talk about in section 7. We don't need to worry about that for section 6. So for lemma 6.6, let's suppose that we have some function that takes some positive real number and maps it to another real number, and it's differentiable such that the integral from 0 to infinity of the magnitude of that thing plus its biggest derivative is less than infinity. If you have this thing, then the limit as time tends to infinity of that function is 0. So let's see, a proof of lemma 6.4. So lemma 6.4 was the thing that we just showed, the collapse down to a single particle. Let's show that you collapse down to a single particle. We are going to define attention as just A. You can see that this is the unnormalized self-attention because we are dividing by n right here. Once again, Q and K don't matter. You can see right here, it doesn't really matter what these are. It's just going to maybe slow things down, but it's not going to affect what happens at the infinite time horizon. So here is the attention, and we've defined it so that it's always positive. Attention is strictly positive. So let's talk about step 1 for clustering. Step 1 is just that we do cluster down to a singular point. Step 2 is that we are going to cluster at exponential speed. So right now we're just guaranteeing that if you have the setup to where everything is on the open hemisphere, that you're going to collapse down to that singular point. So what we're going to do is we're going to take the worst case scenario, I of t. This is going to be a member of argmin, and this is the minimum argument between that W saying, okay, you're on an open hemisphere, and the particle, the farthest particle away from this point saying, okay, you're on the open hemisphere over all of your particles. So pick your favorite time. I'm going to pick time 1 million. And let's talk about the dynamics of exactly what's happening with that particle with respect to this stationary point W. So this, of course, is going to lead to the time derivative of x. And as we remember from far above, can I scroll to it? Hang on, let me just copy that. We are looking for x, I think just USA is going to give it to us, USA. Whenever we go to USA, the definition of x dot, of course, is the projection, and then we have USA right here. So if we delete that and we go back to where we were, we are going to have this x dot, and we are going to have the projection right here, and then we're going to have USA right here, the unnormalized self-attention. Let's get out of that. So we see that we just take that x dot, and that just shows that we are multiplying that projection out, and we're taking the inner product with W. That is the only thing we're doing. We're not doing anything fancy. But what this is going to say is that this thing is going to be greater than 0. This is going to be greater than 0 because we made attention positive. That's just how we defined it. And all of these inner products for x sub j are going to be a larger thing than our worst case scenario x sub I, or it's going to be equal. X sub j might be equally terrible to x sub I. And so that means that this thing is going to be bigger than this thing, our worst case scenario, or it's going to be equal to it, but we're also going to have this multiplier right here. Everything is normalized, so this is going to be between 0 and 1, so this thing is necessarily smaller than this, of course, making this all positive, or at least equal to 0. And this means that x sub I is going to constantly be moving towards W, or it's just not going to be moving with respect to it at all. Which means that if you're on the open hemisphere, we define it so everything starts, initial conditions, on the open hemisphere. As time goes on, it stays on that open hemisphere. That's what we just showed. So we are going to define this function of time now, r of t, R, of course, is going to stand for far, because this is the farthest particle away from this W. It is the minimum argument of the inner product between x sub I over all of the particles and this W. So this is the farthest one out, and it is going to be non-decreasing on the real numbers, the positive real numbers. We're also going to define some R infinity, and R infinity is just whenever you take time to be infinity. And this is going to be just how we've kind of made it to where R infinity is going to be greater than or equal to the initial condition of R, and these are going to be positive by assumption. Just this is kind of how we made them. By compactness, we can say that there exists some sequence of times, t sub k from k equals 1 to infinity. So like this is going to be time 0 to 1, then time 0 to 2, then time 0 to 3, and this grows until it's time 0 to infinity, which is just to say all time. And by compactness, this kind of means that like off the bat, we don't really know if x is going to approach some thing, stationary x bar, I'm sorry. So it might be like sine or cosine, to where like sine starts out to where whenever you take it, it starts at 0, and then it is going to tend to 1 as you get to pi over 2. But over 0 to pi over 2, it really looks like it's approaching 1. But as you increase, it's like, oh, no, it's not approaching 1, it's approaching 0 again. Oh, it's approaching -1 now. And so maybe over infinite time, it could have been approaching -1, but sine specifically is not. But over the specific sequence of time, 0 to pi over 2, it really looks like it's approaching 1. And that thing right there would have an x bar of 1. Do you kind of see what I'm saying? To where we can't assume that every particle is going to approach a stationary point off the bat. We have to show that eventually. And so we create this sequence of times right here. And we have the limit case is going to be the thing that it approaches for all particles. And let's see, so of course we are going to have the R infinity is going to be less than or equal to, moving from right to left, this xj and w. So the point that the particles are approaching is at worst going to be the far function is going to be the farthest particle at time infinity, if you take this infinite time case. So what do? We take the derivative to see how this is going to evolve with respect to time. And so this x dot and w is going to be something to where we take the limit as k tends to infinity. So we can introduce this attention bar, this a bar, which is just the attention for x sub I bar and x sub j bar. And whenever we plug these things in, we can see that, okay, if we pretend that x sub j and x sub I right here are equally terrible, we can just say, okay, well, we can just use the far function in order to show these things. And we want to notice that this thing right here, I think this is from the little caveat that we showed with the thing tending towards 0. The limit, as you take this from t of k towards infinity, so like the kind of space between this t of k limit tending to infinity and the actual infinity, that difference between these two things is going to be equal to r infinity minus this specific limit right here, which is 0. So this thing being 0, as we take this limit, means that the left-hand side of 6.2 is equal to 0. So this thing right here is 0 as you take time tending to infinity, and meaning that this right-hand term is also going to 0. This implies that x bar 1, x bar 2, x bar 3, all of the x bars are tending towards this x star. Every single particle, it means that this thing right here is tending towards 1. I think that's what it's saying. And so because this is tending towards 1, because this needs to be set to 0, this is just going to be some value, and the attention of this thing, 1 minus 1 being 0, that means that every single particle is approaching this x star. And that's what we need to show, to where we kind of needed this as a tool. We no longer need the sequence of times. We just showed from this 6.2 that every single particle is now approaching one singular point. And it approaches that point, and then it gets there, and then it doesn't keep moving after that. That is the infinite time horizon. So we've shown that every particle is approaching x star in a new way, to where we don't have to have the limits on beta. So for step 2, we're going to show that not only are we collapsing to this x star, we are collapsing to this x star at an exponential rate. So let's introduce a function that's extremely similar to the r we just had, but now far is from alpha. So this alpha, the only difference is that instead of going to w, because you were never required to meet w, you were only required to get closer to w. Here we replace w with this x star. X sub I is going to become, it is going to occupy the same space and be degenerate with x star. So this inner product is going to eventually be 1 at the infinite time horizon. We take the worst case scenario at some time, so we take the farthest particle away, exactly like we did before. And what we're going to do this time is we are going to say, okay, so from what came before, we know that x star lies in the convex cone generated by the points, all these points. Like the point cloud of all the particles, x star is not going to lie outside of that. X star is not going to lie in some surprising place off the hemisphere or outside of the convex cone. It is going to be kind of within. It's going to kind of be vaguely like a center of mass, to where it's going to be between all of the particles. It's going to be, well, it's going to be in a convex cone. So we can say that this eta x star is going to be a convex combination of the points, where this means that all of the elements of this are going to be non-negative, and they're all going to sum together to 1. And this is going to imply 6.4, which says that there is some x star, which is made of the sum of all the particles, to where you take some theta, and you modify each particle by this theta, and you sum them all together, and then you achieve this x star. There's some mechanism you can use to turn the particles into x star. For some theta that is going to be, whenever you sum them all together, they're going to be greater than or equal to 1, and each one is going to be positive. There's going to be 1 for each particle. Now we are going to do just like before. We have our alpha. Now we want to know how alpha evolves. We take the derivative using the Taylor expansion and the definition of a derivative. We take this we take this derivative, and we get the same thing we got before. And now we see a very similar thing, which says that this alpha is going to be equal to this x dot. We use the same thing. X dot is going to be the projection times the attention. And here is the worst case thing. So we're just saying off the bat, okay, so this is going to be greater because there's going to be some j. If we just pretend that j is equally as bad as x sub I, then you're going to get this thing. It's strictly going to be greater than that. But on the other hand, what you can say is that this thing right here, let's kind of expand on this. The minimum of x sub I and x sub j, that is going to be less than or equal to this thing based on this 6.4 that we just defined. It is going to be less than or equal to this thing, which can be shown. What we're doing is we're taking x sub I and x sub k, and this x sub k, we are multiplying it by this this theta right here. This is going to turn this into x star because of this theta, and that is going to be our alpha. So this term right here, 6.5, we show that this thing on the inside of it at least contains alpha. So that means that alpha dot is equal to something with alpha in it, at least. So plugging 6.6 into 6.5, merging these two, what we get is that this alpha dot is reliant on alpha in some way. And then we just solve this ODE using Gronwall. By the way, I hope that I'm pronouncing these things at least vaguely correctly. Then we apply Gronwall, and this shows us that alpha is going to be, once we solve this ODE, is going to have this term, which is exponential with t, which shows that you collapse. Not only do you collapse to this x star, you also collapse down to a single point at exponential speed from solving this ODE. And so that's really cool. This is the main point of section 6. This is the main thing that I want you to take away. That now, from Section 4 and Section 5, we found a way to reduce the restrictions of assuming that you have a dimensionality of 3 or greater. That means that you are guaranteed to collapse down to a single point, and you are collapsing down to that single point at exponential speed. That's what we just showed. So as we continue with Section 6, so that's the main takeaway. As we continue with Section 6, we are going to tie up some loose ends. We did this assuming that you were on the open hemisphere, the same hemisphere. Let's just calculate the probability that you actually do that you are on the same hemisphere. So the probability that there exists some W such that you're going to be on the sphere, and the inner product is greater than 0, meaning that you are on the hemisphere for all particles, here is the normalization term. This is the power set of all the configurations that you have, and here is the I think this is permutation. Either way, this is going to be the set of all things of all particles. I'm sorry, the configuration of all initial conditions that puts you on the same hemisphere. So here's all the things that put you on the same hemisphere. Here's all the possibilities total. That's going to give you the probability. And so for 6.2, we are going to move on to a more precise quantitative convergence. And so whenever n is fixed and d tends to infinity, whenever you just have some set of initial conditions, the probability that everything is just going to be orthogonal just raises like a crazy amount. So chances are all of your particles are going to be strictly orthogonal. From here onwards, we are going to start setting up this idea that whenever we start out with all of the initial conditions, they are all going to be, in the perfect case, orthogonal. So initially, each particle is at worst just going to get its own dimension, but as the dimensionality tends to infinity, it's just going to be mostly a sparse space, and each particle is going to be orthogonal to each other particle. And then that's the initial conditions. And then there's going to be the dynamics to collapse them all down to a singular point. So initially, this inner product is going to be 0 because they're going to be orthogonal, and then that's going to tend to 1 as time tends to infinity as they collapse to that singular point. Whenever d is just much greater than n, it's just going to be almost orthogonal. We'll deal with that in just a little while. But we're mostly dealing with the idea that, okay, let's pretend that the initial conditions, let's jump into theorem 6.8. The initial conditions are such that we design everything so that the inner products between all particles at the start is 0. They're all orthogonal. We set up our familiar initial conditions, and then the angle is going to be the same for all particles. So what we're saying is that initially everything is completely orthogonal. Then all of the particles are going to evolve, but all of the particles are indistinguishable right now. If you remember, we set Q, K, and V all to identity. So each particle is indistinguishable from each other one, and so that means that they're all going to evolve in the same way. And so they're all going to evolve in the same way, and they're all going to collapse down to a singular point. So instead of saying like, oh, this is how all of the particles evolve, we talk about each particle and what each particle is doing in order to collapse down to the single point. We just say, no, we just need one angle. All of the particles are going to act in exactly the same way, and they're all going to do the same thing. Let's just talk about this angle. This angle, we're going to name it theta, and then we're going to define this gamma, that is the cosine of that theta. That way, you start out. Whenever you start, let's talk about the unnormalized self-attention. Whenever you start out, this gamma is going to be 0, and then after infinite time, the gamma is going to tend towards 1. At infinite time, gamma is 1. And so the evolution of this gamma, and we're going to prove this down below in a few theorems, in a few proofs. This thing is going to evolve so that there's going to be a 2 right here, because each particle is interacting on another particle, and that other particle is acting on the first one. A acts on B and B acts on A, doubling the force. So we have this 2 right here. We're dividing by n because we have unnormalized self-attention. We have this magnifier. This is essentially the attention. This gamma is now a stand-in for the interaction strength between particles. We have this thing, which is going to start out at just 1, but it's going to shrink down to 0 as gamma tends towards 1. This means that at infinite time, whenever gamma is going to be 1, this is going to end up being 0, so that all the particles collapse down to a single point and then they stop moving. And this is the aggregate effect of all of the other particles, plus yourself. This is the aggregate effect of all of the other particles interacting on you. And so that's what we have. So now, instead of saying, oh, let's talk about all n particles, we're just talking about this gamma. This gamma tells us all about the evolution of the dynamics of the entire transformer. And that's really cool. So from here on out, we're going to use the torus instead of just saying the real numbers, or saying that we're on the sphere, I suppose. Either way, we have a torus now. And we have theorem 6.9. So this is going to... Oh, yeah. So we're not actually going to have pure orthogonal things. They're going to be almost orthogonal. Whenever we have the more realistic case, d is much greater than n, we're going to have a bunch of almost orthogonal initial conditions, probably. So if you actually sample these particles, there is some probability that you are going to be on the open hemisphere. So this is the probability of that. So with this probability, then you're going to have some almost orthogonal situation. And what we're going to do is take this almost orthogonal situation and subtract it from the purely orthogonal situation. So here's the difference. 6.11 is kind of the difference between the almost orthogonal and the purely orthogonal case. And this is going to be less than or equal to the minimum of these two things. So whenever time is small, this is going to dominate, and this is just the regular variance that you would expect with IID in some dimensionality. And then you have this 2, because there's two particles interacting with equal force, equal and opposite. Then you have this term right here, which is in the appendix. Feel free to jump over and read Appendix D. I'm not going to be going over the appendices, but apparently this comes from the Lipschitz nature of the vector field. So whenever t is small, this term here is going to dominate because d is going to be a very large effect. And whenever time begins to increase, the smallest term is going to end up being this right here, as time grows very large. And so the difference is shrinking between the almost orthogonal and the purely orthogonal case. And that's kind of what we're saying on 6.11. And now let's prove this gamma thing. So the idea that if you start out purely orthogonal, and then you evolve down to a single point, that you can just talk about gamma, just one parameter instead of all of your particles. So we come back to the angle theta. We say that there does exist some theta that is a member of the Cauchy solutions, such that this thing absolutely holds for any distinct pair of particles. And what we're going to be doing is just renaming things. This is just going to be a change of basis. So whenever you have your initial conditions and everything is orthogonal, just consider the orthonormal basis, E1 to ED, such that xi gets E sub I. So E1 gets x1, E2 gets x2, and so on for all of your particles. By decomposing this into this new basis, by this change of basis, we call this basis permutation p sub pi, such that you just go from the sphere onto the other sphere. We're literally just renaming things. That's all that we're doing. So this permutation acting on this space is the exact same as taking the entire space and saying, okay, let's just talk about the space with respect to this new basis, this permuted basis. And so that is the essence of the proof. We are just going to rename things. Now, E1 gets x2, and E2 gets x1, and so on. We're just changing the names. We're just permuting the basis. And so what we're going to be able to say is that this inner product that you initially start out with is going to be equal to saying that, okay, so this means that if we permute the entire space, if we permute everything, then that's equal to saying, because we have particles that are exactly the same in this toy model, we can say that these indistinguishable particles, we can just rename them. Now these are just the permuted particles, because they all act exactly the same. And this is true for all pairs of particles. So instead of saying that, oh, we were dealing with x1 and x2, you may as well have been saying you're dealing with x1 and x3, or x1 and x4. So this means that the interaction between all particles is exactly the same. And this is going to conclude the proof. All particles are acting exactly the same. They're evolving in exactly the same manner. They're starting from equally orthogonal positions, and they're collapsing to the singular point. So the gamma is a valid thing to use. That is our proof. So for part 2, we are going to have the curve gamma. So what we're going to want is just the time derivative of this thing. So for the case of self-attention, we have this x dot is equal to this projection right here. Or, I'm sorry, this is just the projection. This is just the definition of a projection. This is what we've been dealing with the entire time. Then what we're going to do is we have x sub I and we have x sub j. We're going to introduce x sub k. We're going to introduce a third particle. And this gamma dot is going to be equal to 2 times x dot and xk, the inner product there. And that can be expanded out into this thing. This inner product can be written as, here we have regular self-attention, here is our z, and we have the this projection right here. And now what we're going to show is that you can take this thing, and here the step we did across the page is we take z and we remap z in terms of gammas. And that's the step that we took. This is still exactly the same. And then what we can do is we can say, okay, so we have that in terms of gamma, but each of these things can also be mapped out in terms of gamma. So there's going to be a few cases here. We explicitly said k does not equal I, but I could equal j and k could equal j, and none of them could be equal. So you take those possibilities, you can multiply these out and FOIL them, and what you get is this thing right here. You can remap each thing in terms of gamma, and that gives you this. And this function, along with this c, gives us exactly what we saw earlier. I'm not going to scroll up. I'm going to take their word for it that it's the same. You get that this gamma dot is the same thing that we just saw a little while ago, just by taking the derivative and working out the mathematics as desired. So for 6.3, metastability and a phase transition, we're going to introduce this, this gamma. So one really interesting thing that we're going to be able to do is talk about a phase transition curve between particles are not collapsed and particles are collapsed. So we're going to take some initial sequence, and we are going to say that we have some error term, delta. And this is going to be positive, but it's going to be much less than 1. So we're going to introduce this function here, and this is going to start telling us about the probabilities, or at least the case of, are the particles collapsed in this specific regime, given some dimensionality, given some beta, and given some time. The way that this is going to work is we have the probability that everything is on the same hemisphere, and we have the this probability is going to be equal to the probability that the inner product between these two things is 1 minus this small error term. Everything is pretty close to 1. This is the almost orthogonal case. So here is the probability that we are in the nearly orthogonal case being equal to the probability of everything being on the same hemisphere, or at least that's what I think is going on. And we are going to take t as equal to the minimum argument over the time s. And so what we are going to get, we're going to take the partial of that, and that gives us our gamma. If we take the case that everything starts out completely orthogonal, and everything is going to collapse down to that singular point, whenever we take the infinite dimension case, we are allowed to approximate this by just saying that gamma is equal to 1 minus delta. And so this is going to introduce a really cool thing that it talks about right here, but I'm just going to talk to you about it using this. So there's two things that we are mapping out. There is this gamma right here, which does not specify specifically that we are going to say that time tends towards infinity. So we have this 6.12, which uses this gamma. It uses the approximation that we had that everything is completely orthogonal and sends it to infinite dimensionality. And then we also have this gamma right here, which does not do that. And so what they do is they sample this gamma a bunch of times, and you get this graph talking about, okay, you've got your beta right here on your y-axis, you've got time going horizontally, and you've got some dimensionality going. And on the blue is whenever there is no clustering. Your inner product is going to be 0. And then on the red over here is whenever you have a very, very, very high probability that everything is clustered together. But let's look at the d equals 2 case, top left. You can see that there's this entire white regime right here. And we can also see the black bar, the 6.12 that we just said, using a couple of assumptions. So this white regime is going to be the case to where the particles are going to start clumping together. They call this the metastable state. There's going to be this metastable state where points are clustered into several groups but eventually relax. So the particles are going to start out as their initial conditions, just spread out onto the surface of the sphere. And then they're going to cluster together into small metastable states. And then over the infinite time horizon, or here, just wait 5 seconds or 5 iterations, then they are going to collapse down to a single point. And it shows that this regime, this metastable state regime, gets smaller and smaller and smaller as you increase the dimensionality. But that's the main idea, to where this phase transition is actually showing us, oh, there is a third phase based on what we've been talking about, which is this metastable state phase. And that's really fascinating. This graph, this visual, is the main idea of this phase transition, the introduction of these gammas that we've been talking about. And this is the main point, that there is this phase transition and you have these metastable states. Oh, let's scroll back up because I want to talk about problem 1. So the paper actually asks some questions as it goes along, which I think is really cool. There's a few unanswered questions. I think that it would be a whole lot of fun to answer them, and I am actually working on my humble attempt at trying to solve a couple of them, so hopefully those end up well. So for problem 1, do the dynamics enter a transient metastable state in the sense that for all beta much greater than 1, all particles stay in the vicinity of m is less than n clusters for long periods of time before they all collapse to that final cluster x star? And so that is the first problem that is proposed, left as some work for the reader. Then problem 2 is going to, one may also naturally ask what general QKV are going to do. So problem 2 asks, can the conclusions of theorem 6.8 and theorem 6.9 be generalized to the case of random matrices, Q, K, and V? This is a really interesting question, but I also think it'd be really interesting to not say random matrices, but trained matrices. What do transformers do whenever they're trained? Do they manifest some specific thing inside of the dynamics? Do they want to be in some regime that's actually given here in this phase transition chart? Or is there some evolution as you move through the layers, as you move through time? Really interesting question. And that leads us into part 3 for further questions. So part 3, further questions, is going through and saying, okay, so we talked about the attention mechanism, we talked about self-attention, and we found that it can be interpreted as a particle system that is going to collapse everything down to a single point. Now we're going to extend this, we're going to relate it to certain other cases, and we are going to talk about some interesting things and some other open questions that are pretty interesting. So let's jump straight into section 7, where that is going to be down here. We are going to be talking about the Kuramoto model, which we are actually going to see here. It is just going to be the special case of setting d equal to 2 and working on the unit circle. This is going to be really interesting because we actually kind of talked about this in figure 2. whenever there was all the green. It should jump out at us. It's very green. It's below that. There we go. We found it. So whenever here, if we remember, we had the dimensionality of the attention, and our beta. Whenever the dimension was 2, we only had results whenever beta was less than 1 or greater than n squared over pi squared. So what happens in this middle area? What we're going to find is that essentially it is going to be probably getting trapped in a metastable state in the difference of the phase transitions. There's going to be some phase transition that it gets trapped in infinite time. But, more interestingly, whenever we set d is equal to 2, it is going to be a special case. If you set beta is equal to 0 and d is equal to 2, you have a special case of the Kuramoto model, which is the synchronization of oscillators, which is really fascinating. So let's set this up. We are working on d equals 2, and this is going to be basically the same as whenever we were talking about gamma. Now, instead of the theta that we had before, talking about some high dimensional angle between particles, now we just have the familiar cosine of theta and sine of theta for the horizontal and vertical components on this unit circle. So E1 is going to be the horizontal component, E2 is going to be the vertical component, of course. And whenever we take cosine theta is equal to the inner product of our particle and that horizontal component, we differentiate that in t and plug that into our familiar USA, and we get this theta dot, to where now, because this is the unnormalized self-attention, we are dividing by n, and we have this familiar attention bit and the projection. So here we are going to, we'll come back to this in just a second, actually. So the inner product between two things can actually be shown to be this cosine and the difference between the angles and the cosine of that. And we are going to do just like we did with gamma, to where we take this theta dot and we take it from the inner products. Let's scroll all the way back up to see this was made of inner products before, and this was made of inner products, and now, instead of mapping it to the functions with gamma, we map it to trigonometry. And using elementary trigonometry, what we can do is just reduce this in order to just get this this single sign and the difference of angles, and we have our evolution of the particles right here. There is, of course, going to be, we're dividing by n. We have the unnormalized self-attention. We have this interaction strength right here. If you look, as the angles become closer together, then the difference between these two things is going to be close to 0, setting cosine to 1, increasing the interaction strength. And that means that particles closer together are going to be accelerated towards each other faster. This sine of theta sub I minus theta sub j is just saying, okay, I is going to be going into the theta j direction. Normally this would send it in the wrong direction, so we have this negative out here that solves everything, because well, really just because the derivative of cosine is negative sine, but you know what I mean. So we are going to show that the case beta is equal to 0 is exactly the Kuramoto model. And so we are going to define h sub beta as the torus being mapped to a real number as h sub beta of theta is equal to e to the beta cosine theta. And so, oh, just keep this in your head, because we're going to need it in just 2 seconds. Just think of that, and then the derivative is just going to be, it's just going to be the derivative as we talk about h prime. So we can take this and we can define some nu of t as our familiar delta Dirac representing all of the particles, and take this as the measure on our torus t. And the solution to the continuity equation is going to be this familiar thing right here, just like we dealt with earlier in the paper. And we are going to have the vector field as 1 over beta h prime times nu. Except this isn't actually times. This is going to be the convolution on a torus. This is going to naturally want to use a convolution because each particle is going to be moved with respect to the other particle. So it doesn't just matter where your theta sub I is, because that's going to be moving towards theta sub j. We also care about where theta sub j is, and that means that using a convolution here is a natural tool. And so we can say that this is going to be the vector field for unnormalized self-attention, and with self-attention we just have our z baked in, and that is going to manifest as h sub beta convoluting with nu. And so let's talk about the Kuramoto model. So the Kuramoto model is defined right here. It is the theta dot is now going to be some omega. This is going to be our natural frequency of each particle. We are going to have n particles. These are not really particles here, they're oscillators. N oscillators with natural frequencies omega sub I. And there's going to be some coupling strength k. And here we just take something similar to what we just had before. This is positive sign, theta j minus theta sub I. And this k, this coupling strength, is going to determine if everything is going to march towards the same frequency. And so we can say that for a sufficiently small coupling strength k, the oscillators theta sub I do not synchronize in a long time, but if it is strong enough, they are going to synchronize in the long time horizon. Yeah, we would lead to a synchronization of a fraction of the oscillators. It should be total. Oh, it's total if it's big enough. Okay, yeah. So if we take that theta that we had just before and remap it to theta sub I minus omega t, then we can talk about the gradient flow for the Kuramoto oscillator. And so this is for the Kuramoto oscillator, and we have this energy right here. And this energy is going to be, it's just going to be this thing. What we can do is we can come back to our, we can come back to our dynamics of the attention model, and we can say, okay, so we have something very slightly different. Our energy had that, well, let me highlight it for you. Our energy had this exponent. I scrolled too far, I think. Yeah, right here. This beta, it had this of e to the beta cosine theta. So we just set beta is equal to 0, and then this is going to be mapped to the same thing. We have to swap out this j and this I, but that's no worry. That's just, you can see j minus I instead of I minus j. So we're just eating this negative, just moving it around. So it is the same thing. And for us, whenever we set that beta to 0, we get the Kuramoto oscillator. But if we don't, then we get this energy right here, which is still dependent on beta, and you get this thing here. And we are going to be energy maximizing. The Kuramoto model as well as our attention model both try to maximize the energy in order to become a synchronized oscillator. And that energy is maximized whenever your theta sub I is equal to some theta star, where that theta star is going to be the frequency that all of your oscillators are collapsing to. It is going to be the frequency that all oscillators synchronize to. And so in the spirit of this thing here, we suggest the following open problem. A critical point is called a strict saddle point of E sub beta if the Hessian of E sub beta at these points has at least one positive eigenvalue. So with the exception of the global minima, are all critical points of E sub beta strict saddle points? That is the question posed for, of course, problem 3. There is also an extension of the Kuramoto model of this form here where everything is the same except for this h. We take a cosine and we remap it to h, where h is just a nonlinearity that maps the torus to a real number, which we are technically a part of. We have this e to the beta cosine difference between angles. Now, for us, they don't solve it in this paper. That would go a little bit beyond the scope of what this paper is trying to do. We're just talking about interesting correlations. But for this thing here, you can actually talk about it as a modified Bessel function of the first kind. So, section 7 is really interesting because it's essentially saying that you have your synchronization of oscillators, which are attention mechanism. We can form a special case of the attention mechanism and show that it is a synchronization of oscillators. Can we think of attention as a high-dimensional representation of the synchronization of oscillators? What relationships actually exist here? Like, clearly there's a mathematical relationship if our attention can be mapped as a Kuromoto oscillator, a special case of it. That's really interesting. But that is all for section 7. Let's move on to section 8. For the BBGKY hierarchy, what we can say is, alright, what if instead of taking every single particle and using that to derive how the field is going to function, what if instead we track a subset of particles, a group of particles, and we track the statistics of those in order to find the important statistics of subsets in order to talk about the collapse? So we are going to apply this BBGKY in order to get these rows. And these rows are going to be these subsets of thetas. We're going to stay in the 2D situation that we were just working in, and we're going to keep talking about the angles between particles. So if we do this, what we can say is that we have this rotational invariance, which means that if we take the entire system and rotate it, that doesn't change the angle between particles. And with that, we can say that there is some psi that, of course, maps the torus to the positive real numbers, so that this subset right here can be talked about in the same way as psi and just the difference of these two angles if you have two particles right here. Now, proving that clustering in theta is going to happen over the long time horizon is the same as showing that this psi converges to a Dirac mass centered at 0 as t tends to infinity. So, using the fact that this row under BBGKY solves the Louisville problem, using this method, it's possible to show that this psi can satisfy these specific equations. But these two equations have this nu in them. Well, this one has the nu in it. And this nu is going to take this specific form that has this g in it. And this g is going to have this expectation value. Now, we don't actually know what this g is going to look like, we just know that it has this expectation value. So this is going to lead us into problem 4, which is to say, alright, let's figure out the ansatz. Let's devise a realistic shape for g, which allows us to close equation 8.1 right here. And this will allow us to prove the convergence of this psi to a Dirac mass centered at 0 as t tends to infinity. And that is going to lead us into section 9. Alright, for section 9, general matrices, there's going to be 4 specific subparts to this. The main idea is we want to extend the case. We want to say, okay, before we assumed that q, k, and v are just the identity. Now we're going to get away from that. Now we're going to say, okay, what if we take some particular cases and kind of say, alright, let's let these things be a little bit more general, or let's expand our ideas a little bit. The first one, there's going to be 4 subsections. The first one is the repulsive case, where we set v to negative identity. 9.2 is going to be pure self-attention, where we take away layer norm. We're no longer required to be on the surface of a hypersphere. 9.3 is going to be to where we take beta and let it tend to infinity. And then the last one, 9.4, is going to be called diffusive regularization. So let's talk about these. Let's start with, I think 9.1 is a good place to start, the repulsive case. So what we're going to say is, alright, we had this energy here. Before we were trying to maximize it, right? What we wanted to do was say, alright, we take the energy, whenever we maximize it, maximizing it means that the inner product is as big as possible, and that means it tends towards 1 because everything was normalized. So we want to collapse everything down to a single point. Now, we're doing the opposite of that, so it's going to spread out. If you have an infinite number of particles, what you're doing is you're saying, okay, it's going to take the uniform distribution over the surface of the sphere. But we are going to have a finite n. So we're going to change it up a little bit. We are going to have our energy as this thing right here, as the sum of n Dirac masses, similar to how we set up our empirical measure from before. And whenever we minimize this E sub beta over the initial conditions of the surface of the sphere, what we find is that we have a sphere packing problem. And this is from sphere packing problem and coding theory. We have these two things that are, well, they're similar things. They're from the same place. For our mu, our empirical measure, that was just the, where is it? We wrote it down somewhere around here. It is just the sum over all Dirac deltas. Oh, it's similar to this. It's kind of like that, except there was a Dirac delta. I hope you remember from earlier in this video or earlier in this paper. What we are going to do is we are going to introduce some set of support points, C. And what we're going to say is, okay, so this is a member of the surface of our hypersphere. And this pound symbol, this hash, is hash C is the cardinality of n. So it is going to be something with cardinality n. So we could say the energy of the empirical measure is the same as the not energy, the h sub beta, of this C. And then we are going to be able to write out this thing that we wish to minimize. And some in CK07, they characterize the global minima of this C of h sub beta. And so we are going to introduce this definition. Let n be greater than or equal to 2, and let some set of points C from x sub 1 to x sub n be on the sphere, and call it a spherical t-design if the total integral, the integral over everything, of your polynomials p over d variables with a total degree of at most t, if that integral comes up to this thing right here, this summation, then it is going to be a sharp configuration. That is, if there are m distinct inner products between pairwise distinct points in C for some m is greater than 1, and if it's a spherical 2m minus 1 design. So out of CK07, we are going to have a special result, specifically from their theorem 1.2. And this leads us to theorem 9.2. Let the number of particles be greater than or equal to 2. Any global minimum of this h of b that we just bought for that we just created for the energy that we're trying to minimize, any global minimum of h sub beta along the C that we just made is either a sharp configuration or it's going to be the vertices of a 600 cell. And that helps narrow it down to two specific cases. Not super simple cases, mind you, but two cases. A complete picture of the long-time behavior of transformers in the repulsive case remains open. And that's it for the negative energy case. It is a sphere packing problem. Here is one path you can go down, but it, of course, remains an open problem, like these are all going to be. Alright, so 9.2, pure self-attention. What we're doing here is saying that before we constrained ourselves to just staying on the unit hypersphere, but not anymore. What we're going to do is we are just going to remove the projector P so that the attention that we have literally just says, okay, you're not on the unit hypersphere, you can just go into the bulk. You can just go anywhere. And so let's see what happens. First of all, if you don't do any rescaling, then every particle is just going to shoot out into infinity. To make a very rough analogy, 9.1 here, let's take this. 9.1 is the attention. Yeah, here you can see that this pure self-attention right here essentially means that you have delta Dirac instead of having 2.5, where 2.5, that's what I meant by the attention. That's the one that I meant to find at first. Let's go by this one. Whenever we go here, we're back. So if you don't rescale your particles, they just shoot out into infinity because they kind of follow this x dot is equal to x sub I. So every particle, at least over the infinite time horizon, x dot is going to equal some x star, or is just going to be approaching something, which means it just goes on forever. It just keeps moving. So what we're going to do is we are going to, of course, if you solve this, you get this thing. So we're just going to scale by this. We are going to define this z, and this z is our rescaling. So whenever we do that, we can now redefine this attention as this z dot, and this is going to be the difference of z's, where you have your rescaling z's right here. And now what we're doing is the values, that's going to be a difference between two things. Everything is going to be rescaled. And this actually gives you some interesting dynamics. This is actually going to be pretty cool, to where you have this z right here that we see over here, just to make sure things are nice and well taken care of. But what we're going to find is that we have a few different cases of what happens whenever you allow yourself to be in the bulk in general, but you have this rescaling factor to make sure that things still are, well, they're rescaled, so you can take care of them. So you're exploding things, but you're zooming to scale exactly as fast as things are exploding. For v, if v equals id, then what you have is your qk is going to be positive definite. All of your eigenvalues are going to be positive. And what happens is, in the limit, as time tends to infinity, you don't just collapse to some x star. You actually collapse to the vertices of a convex polytope. You have some more interesting geometry of what you collapse to instead of just a regular point. And all of these things are going to be in GLPR24. And if you just take the case that v gives you some eigenvalue, and this is going to be like just the dominant eigenvalue, there's going to be one major eigenvalue, then your limit geometry is going to be the union of three parallel hyperplanes. And for v being paranormal, you are going to get this similar thing to where qk is going to be positive definite, and your limit geometry is going to be a polytope by these subspaces. They also have the v equals negative id case, where essentially everything is just going to die. The dynamics are just going to stop. And you are going to collapse down to a single cluster at the origin star. So here's that star. All results except for the case of v equals negative identity hold for the time-scaled dynamics of 9.3. And this essentially just goes over the exact same information that we are still going to have with this z. We're still going to have a good convex hole because we're taking the convex combination of these attractors. So z is going to shrink and converge to some complex polytope. Then here is the bit about the eigenvalues, and roughly speaking, the coordinates of the points z sub I along the eigenvector of v corresponding to that eigenvector quickly dominate the matrix coefficients p, which is our altered attention, due to the factors of this exponent right here, or this exponential thing. So they have more information here, and this leads us to problem 5. Is it possible to extend the clustering results of table 1, this table right here, to other cases of QKV, and what are the resulting limit shapes? And so that's problem 5, and leads us into 9.3. Alright, for these singular dynamics, we are asking what happens whenever we take the limit as beta tends to infinity. So let QKV be given d by d matrices, and for some b is greater than 0, we consider the system of coupled ODEs, this thing, this difference of things, similar to what we just had before. And we have some z that ties it all together, so everything is nice and normalized. For any t greater than 0, and any fixed initial condition of z, as beta tends to infinity, we expect the solution of 9.4, the time evolution, to converge uniformly on 0t to a solution of this thing right here, where c is going to be following this bit. But the thing is, defining a notion of solution to these two things is not straightforward. So what we're going to have is example 9.3, which more or less just shows that these things are not easy to solve. So suppose that d equals 2 and n equals 3. And what we're going to do is we're going to have just q, k, and v equal to identity, and we're going to build an upside-down triangle. So z1 is going to be top right at 1, 1. Then we are going to have z2 at top left, negative 1, 1, and then z3 at 0, 0 at the origin. Consider the evolution of these particles through these two equations. And so what you're going to find is that z1 and z2, the top of the upside-down triangle, do not move because it's easily seen that c sub I of t is equal to I for I between 1 and 2. The dynamics just, they don't move. So on the other hand, the point z3 can solve either of three equations. z.3 is equal to the difference of z1 and z3, or z.3 is equal to z2 minus z3, or even z.3 is equal to 1 over 2 z1 plus z2, all minus z3. In any of these cases, either of these two things remain satisfied for almost every positive time. So, is it possible to prove the existence of these solutions defined in the sense of Filipov 15, which says, we thank Enrica Zuaza for the suggestion. We can either use a time discretization for this, or use a convergence argument for the solutions as beta tends to infinity. Uniqueness, however, does not hold as illustrated by example 9.3. This naturally leads us to the following question of problem 6. Is it possible to establish a selection principle similar to viscosity or entropy solutions for solutions to 9.5 through 9.6, which allows to restore uniqueness? If yes, it is possible to revisit the clustering results of GLPR24 and problem 5 in the setting of 9.5 and 9.6. So that's kind of the question to where how does it work as beta tends to infinity? But that is going to lead us to 9.4. So for 9.4, diffusive regularization, we are going to stick with equations 9.5 and 9.6. And so what we're going to say is that these are also an original model for collective behavior. So there's some similarities in spirit with something called consensus-based optimization, or CBO. And in CBO, what we're looking to do is we want to minimize a smooth and bounded, but otherwise arbitrary function f, which maps the real numbers of some d dimension to some real number, by using the Laplace method, which we can see here. And this takes the infinimum of some function given some parameters. And this is going to be accomplished by considering this particle system with these dynamics, using these parameters. So there's going to be some point nu of mu, and this is going to be a weighted average of the particles, this right here, and we're going to have a partition function. And morally speaking, these particles are going to be near a minimum of f if they have a larger weight. Or, I'm sorry, these particles that are near the minimum of f have a larger weight. So they're weighted towards the thing that we're looking for, the minimum of f. The drift term is a gradient relaxation. And let's see. The results of convergence to a global optimizer do exist under various smallness assumptions on the initial distribution of the particles and assumptions on the relative size of the coefficients. They also rely on the analysis of the associated Fokker-Planck equation, and they point out that they said earlier that this is mainly in spirit because these results and analyses are inapplicable to what we're dealing with because we have no analog for f of x. But they do raise the following interesting question, which is problem 7. What can be said about the long time limit of transformers with a noise or diffusion term of strength sigma, which is going to be positive, greater than 0? And that leads us to the final section, section 10. So for the 10th and final section of this paper, we're finally going to talk about what neural networks kind of do. So, we've talked so far about the evolution of the particle system, but this is for the general dynamics as you ascend through the layers of a neural network that has all of its weights just set to identity. So, what does the actual trained network do? This is a massively open problem, and one that's being tried. They're attempting to solve this in many different ways. But what we say here is we say that expressivity of the neural network, the ability for it to actually have a wealth of a output space in natural language, is mainly due to two things, or at least it can be broken down into two parts: interpolation and universal approximation. Those are going to be two key ways that you can create your output space of usually natural language. So for discrete time transformers, the universal approximation has been shown to hold. And in the context of flow maps, it's understood that interpolation and approximation reflect the controllability of the system. But besides just approximation, actually understanding not even just the training dynamics of transformers, but also just the dynamics of the trained transformer. These are both major challenges that they're not covered in this paper, and they're not solved problems. We are still working as hard as we can to try to understand how these neural networks function, because they're really, really cool. They're extremely interesting, but also because it's extremely important. If we understand how transformers actually function, if we understand how they work mechanistically or in any way, then we can guarantee they're going to be safe. We can guarantee that whenever we put them out into the wild, they are going to work in a way that we think is a good idea. They're going to benefit people instead of potentially not benefit them. So this is understanding transformers is still an open problem, but this is a really cool paper that I enjoyed thoroughly. That is the end of the paper. I will not be going over the appendices, and I hope you enjoyed this video, and have a good day.